Right, so let's start the last talk of the session. So it will be by Abhishek Shetty from Berkeley, who's going to talk about smooth analysis for sequential decision making.
Yeah. Oh, shall I start? Everything okay? Okay. Yeah. Hi. Yeah. Thanks for coming to my talk. Today I'm going to talk about smooth analysis for sequential decision making. This is joint work with Nika, Tem, Yanjan, and Kunha. So let's dive right into the problem that we are interested in. The problem we'll look at today is sequential prediction. It works as follows. So there's a learner. And there's nature. The stochastic version of this problem works as follows. There's learner and then there's nature. And at each time, nature draws a xt from some distribution d. And the learner observes this. Then the learner predicts a y hat t, which is, let's say, is Boolean. Then the nature gives out the true label. And this repeats for t steps. And what you want to do is compete against a given set of hypotheses. In this context, a hypothesis is a function from is a Boolean function, a function from a domain to plus minus one. Also, please feel free to stop me whenever. And the notion of the thing that we'll aim for is regret. So far we've been seeing a lot of competitive ratio. So here we look at something slightly different, which is regret. This is the loss of the learner, which is in this setting is measured as the number of mistakes that you make, number of y hat t's that don't agree with y t's, minus the loss of the best hypothesis in hindsight, which is the best predictor in the class, and you're comparing to the number of mistakes the best predictor makes in hindsight. Okay, so this is the stochastic setting. The more sort of famous version for regret is the adversarial setting. Here again you have a learner and now you have an adversary. The adversary gives you an arbitrary xt, and again the predictor, the learner makes a prediction y hat t, and the true label is revealed, and this repeats for t steps. Again you're competing against a set of hypotheses, and your regret is measured the same way, which is the number of mistakes you make minus the number of mistakes the best hypothesis in hindsight makes. Is the setting sort of clear? Sorry, both of them are sequential, but the previous one was random, where the data was generated from a distribution. Yeah. Any other questions? Okay, so the adversarial setting is nice and it captures a lot of problems, but the issue is that you can't do much even for simple classes like binary, like thresholds on like a unit domain. You can get high regret, like you get basically infinite regret, and the counterexample is easy to see. So let's say you have a learner who has to decide whether you have to go left or right. Let's say the learner says he wants to go left. The adversary then says no, you have to go right. Then again you make a decision the next day. The learner now says you want to go right, but the adversary says oh no, you need to go left, and this happens again, and this keeps happening. But you might think that the benchmark that you're competing against is really complicated, so maybe you still can get good regret, but turns out there is a good classifier in hindsight that makes no mistake. So you basically get, sorry? You can show, okay, so this was a deterministic algorithm. This low bound directly implies deterministic algorithms maybe, but you can show even for randomized algorithms up to a factor of 2, it's you can't do much better. Like there's a difference of 2 because you can randomly guess, but that apart you can't do much. Does that make sense? Okay. Okay, so what is the complexity for these problems? In the stochastic setting, this is fairly well understood. This is a famous result from maybe 50 years ago now. It says the regret is bounded by square root t times the VC dimension of the class. If you don't know what VC dimension is, it's not important. For the setting, VC dimension is something small for essentially any class that we are interested in. The adversarial setting is also well understood in the sense that we know the characterization of the regret bound. This turns out to be another combinatorial quantity called the Lilstorn dimension, Again, it's not super important what it is precisely, but for essentially any class you can think of, this number is infinity or like really large. So it tells you that for any class, this the regret that you can get is you can get only trivial regret bounds in the adversarial setting. You can also ask about the computational complexity of these problems. Here the setting is more interesting, but at least what we know is that empirical risk minimization achieves good regret bounds. And also you are dealing with average case inputs, and in these sort of learning settings, we know a lot of heuristics that work for real world instances. The corresponding question for the adversarial setting, the inputs by definition are worst case, but you can also show that even if I can solve the empirical risk minimization problem, the getting regret is computationally difficult. So there is a certain sense in which both statistically and computationally you can't do much in the adversarial setting. Okay, so what do we want to do? So the stochastic setting is great. You get clean statistical rates, learning reduces to optimization, and it's a good model for many settings. The concept, this is a very strong modeling assumption, and it's not, by definition, it's not robust to corruptions and manipulations. The adversarial setting, on the other hand, is great. We are making no assumptions on the instances, and you are capturing correlations between the past and the future, and it's arbitrarily robust to corruptions. But the issue is you have computation and statistical interactability, and it does not incorporate structure, and it's in some sense overly pessimistic. The question we want to sort of talk about is, can we bridge between these two settings? Okay. So one thing we want to sort of do is go between the two settings. We want to look at situations where these sort of sequential predictions actually come up and try to capture what properties they have. And one thing that turns out to be really important in many sequential decision-making problems is the dependence of future instances on the past and the actions of the adversary. This is something that you want to capture in whatever model for beyond worst case adversaries that you're building. And also the other thing is real world instances are inherently noisy. So maybe we can incorporate noise that is inherent in the inputs. And the ideal goal would be to capture properties of real world while getting bounds similar to the stochastic setting. So this is what we'll aim for. And the model we'll look at is the smooth adversary model, which again is similar to, the setting is similar to the before. There's a learner and there's an adversary. The adversary gives you a point x hat t, but we'll think of there has to be inherent noise from nature, and the instance xt gets perturbed by eta t, which is some small amount of noise. And as before, the learner makes a prediction y hat t and receives a true label yt. Again, the regret is defined as before. It's the number of mistakes that the learner makes compared to the number of mistakes, the best hypothesis in hindsight on the noisy instance makes in hindsight. Okay. So the motivation for this is that, it's the same definition of regret as before, but instead of xt, you have xt plus eta t. Okay. Are there any other questions about the setting or about the? That's exactly correct. We'll look at a slight generalization of this, which is easier to sort of think about. But yes, you're right. Like xt is adversarial, but there is some noise. This is like similar to sort of standard smooth analysis, algorithm analysis. Are there any other questions? If the noise is small, that is correct. So we'll get some bounds that depend on the noise rate. We'll see what exactly it is, but for sufficiently small noise, I guess. Are there any other questions? Okay. So captures the noise in the setting, but The other thing which it captures is because the adversary is otherwise arbitrary, you still are capturing correlations across time steps, at least. This is something that's being maintained. So it turns out it's easier to, instead of dealing with the X plus noise, somehow it's easier to deal with the setting where there is a XT comes from an adversarial distribution that does not put too much mass on one single point. We call this smooth distributions, where the density with respect to some base measure is bounded by some constant, which we'll call sigma. It's easier to deal with this setting than the noise setting, and it's somehow more general. This distribution is fixed. I mean, yeah, it's fixed. Like, let's think of it as a uniform distribution on some domain. It's fixed, but like the adversary's distribution can't put like too much mass on one. Like, it's somehow saying he can't put too much mass on one point because the uniform distribution doesn't put too much mass on one point. So if you add some adversarial point and add some noise, you'll get the same thing, but it's some generalization. Are there any other questions? Okay. Okay, so the question we are interested in is what is the complexity of smooth online learning? In a paper couple years ago, we show that for any class in the sigma smooth adversarial model, the regret is bounded by square root t times log 1 over sigma times the VC dimension. So what it says, I guess, is that as you change this noisiness parameter, you interpolate between the average case and the worst case, but like as long as the sigma is somewhat reasonably 1 over sigma is reasonably small, you get like VC dimension dependent bounds. Right? Okay. Is there any questions about the bound? I'll quickly go over how to prove this. So the idea is to replace, okay, so in your head, you should always think of f hat as being infinite, because like that's where VC dimension becomes interesting. Otherwise, you could always apply union bound. So f is like infinite, and you approximate f with some other smaller class, and then you can run a no regret learning algorithm on this. So if you do that, you, on the smaller class f prime, you will get a like sublinear regret, which depends on its size. But the challenge is how to bound the difference between f and f hat. Yeah, because your data is still somewhat adversarial, you still need to bound the difference between these two things. And this, okay, believe me, will reduce to the following sort of empirical process type question, which is that you are given a family of functions which have small expected size under the distribution, and you want to bound the expected max of the sum of x evaluated on g evaluated on x, where x comes from arbitrary sequence of sigma smooth distributions. This is supposed to capture the approximation error. Okay, this seems like a standard thing to deal with, but the issue is x1 to xt are not independent. They because they come from this adaptive sequence of like adversarial points. These are not independent. So dealing with this is a challenge. So the main way we deal with this is that we show that an adaptive sequence of smooth random variables can be simulated by a larger set of IID random variables. More formally, we show that for any sequence of smooth distributions d1 to dt, there is a coupling between draws xi from di with draws zi from the base measure mu, such that with high probability xi is contained in the set of z1 to zi. So in some sense, that the randomness in the smooth distributions can be captured by the randomness in from draws in mu I. Using this, you can show the empirical process bound that we wanted to show in the previous step. Does this make sense? Maybe this was a little too fast, but it as long as a high level intuition was clear. Yes. Okay, yeah, sorry. K is a number that's it's a parameter. Let's think of it as like 1 over sigma or something like that, which is the smoothness parameter. Are there any other questions? Okay. So far what we have seen is that smooth online learning is, at least in bounds, is approximately the same as stochastic learning. The next part we'll see is what about the computational problem? Yes. Uh-huh. They still have to be conditionally smooth given the past.
Right, it's x1 plus some uniform.
Uh-huh. No, so I mean roughly, okay, maybe
because these are all in the interval 0 to 1.
let's say they're all in the interval 0 to 1, like because they have a small amount of noise with some good probability. Let's say you take some point and you are drawing uniform around that point. With some good some probability, a uniform random variable will fall in that interval. And there's some rejection sampling kind of. That's basically actually roughly the proof. Yeah. Is that convincing? Okay. Yeah. Okay. Yeah. Okay. So the next question is if we can algorithmically reduce sequential decision making to offline decision making. Here the neatest model to think of is the Oracle efficiency model. What it says is that you get access to an ERM Oracle, which can solve the problem of in the class what is the best hypothesis for the data that you have seen so far. This would suffice for the this Oracle would suffice for the offline problem, because from just VC theory it says ERM gets you low regret. So the question is if you could what it's trying to capture is if you could solve the offline problem, can you also solve the analogous online problem? So the setting that we would be interested in is where this number of hypotheses is large, but the space has some combinatorial structure so that you can do this optimization easily. The standard example for this is shortest paths in a graph. There are exponentially many paths, but you can solve the given any weights, you can solve which is the shortest path first. Okay, but unfortunately, you can show query complexity lower bounds that say that there are problems such that even given the ERM Oracle, you cannot achieve non-trivial regret in the worst case. So at least in the worst case, it seems like decision making or sequential decision making is genuinely harder than offline done. Okay, so the question is, does smoothness help in this setting? And what we show, and another result by results around the same time by Shasha's group at MIT show that in the smooth adversary model, there is an Oracle efficient algorithm that gets sublinear regret. In the worst case, you can't even achieve sublinear regret. And it also still depends on the VC dimension. So you can get regret that's similar to what you can get in the offline setting, and with like some mild dependence on sigma. So are there any questions about the result? Okay. Yes. Uh-huh. Okay, so I mean, I guess there are two different settings. Okay, the interesting, I guess, what I mean is interesting in the real world in some sense. The low bound is like it constructs actually somewhat reasonable learning problem. It's it embeds some query complexity low bound, but the problem that it induces is actually somewhat reasonable. Maybe we can talk offline about what the problem is, but the interesting is some two different senses in those two bullets, I guess. This is like interesting in the real world because we're assuming some oracle, and it's not clear why you should assume an oracle, but like what it's supposed to capture is that the number of experts is like really large, so you can't just run multiplicative weights or whatever. But you can solve like hindsight optimal, and the questions, can you get regret even in that setting? Sorry? Right. That's exactly what it is supposed to be. You're given black box oracle to the ERM oracle. Can you get an algorithm that gets sublinear regret? That's the setting. Like it's the oracle is black box. Yeah. The oracles. The last bullet says the answer is no. In the sense there is a problem, reasonable problem, such that even given a black box oracle, you cannot get sublinear regret. Are there any other questions? Okay, so what we show, I guess, is that you can achieve sublinear regret. That depends only on the VC dimension in the oracle efficient model, as long as your adversary is somewhat smooth. Yes.
Maybe the example, the left right example, the game, that is that already. So you're saying even in instances where you put inefficiently
Yes. Yeah, exactly. It constructs an instance where if you're given exponential time, I mean exponential in something, exponential time, you can get square root t times square root t regret. But if you're given polynomial time in this oracle model, you cannot get t over 2 regret. Does that make sense? Okay, so again, let me quickly go over the proof idea. Just to make sure what the algorithmic problem is, the algorithm sees the data so far, that is x1 to x t minus 1. Let's call that st with the labels, and also sees xt, which it has to predict on. And it has an oracle. It has oracle access to ERM. That is, it can input st to the ERM, and it will tell you what the best hypothesis in class on this data is. So that's the algorithmic setting. The first thing to do, I mean, I guess we are working in the smooth model. So the natural, maybe what one could hope for is that you can just run what you do in the average case setting, which is you just run ERM. You can actually show that this has like t regret. Oh, sorry, was there a? You can show that this has like t over 10 regret or whatever. Fairly simply. So this just running ERM on data does not work. So we need to use the fact that x1 to xt are smooth, and one way to do this is again looking back at the coupling lemma to see that the uncertainty in x1 to xt is captured by samples from the base measure mu. This is what the coupling lemma says intuitively, and this leads us to some natural algorithm, which is pick some number n, which is some parameter, and sample n random variables z1 to zn from mu, along with made up random labels y tilde I, and then run ERM on st union the made up data. So if you have seen follow the perturbed leader, this is very similar in spirit to such an algorithm. The interesting thing, I guess, is the parameters of what n is, but we'll probably not get into that right now. So this is the algorithm. It's fairly simple. You just, take the data you have seen so far and then come up with hallucinated data, which somehow is a proxy for the points that you have not seen, and then you'll just run ERM on this and then predict using that. Are there any questions? Mu is this, okay, sorry, maybe I went over that a little fast. Mu is this base measure relative to which you are you're defining smoothness. Let's just think of it as a uniform distribution on some domain. So the smooth setting was where the adversary at each time step is giving xt from some distribution whose density is bounded by some number. So mu is the measure with respect to which it is bounded. So let's think of it as some uniform distribution on some interval. Does that make sense? Okay. So again, recalling the result, we have that you can get sublinear regret with like dependence on the VC dimension in the Oracle efficient model. And you have some nice properties, which is that the oracles work only on the oracle needs to only work on smooth or average case instances. This sort of is important because for many binary prediction problems, you can get like NP hardness in the worst case. So maybe the oracle assumption is maybe not super realistic, but like if you sort of believe the real world is comes up with reasonable examples on which you can design heuristics, the reduction to the ERM still preserves this good instances sort of property. And turns out this bound, somehow the square root in the sigma is important. It's a longer story, but it gives you improved regret bounds for Oracle efficient learning, even in like worst case settings, by taking sigma to be an appropriate to an appropriate limit. Now, like it gives better than known results even for the worst case setting, which is sort of cute. But the model of the story, I guess, is even computationally statistical. Smooth online learning is the same as the stochastic setting. How much time do I have? Oh, I guess I have. I mean, the high-level main takeaway is that the smooth model gives you a model for sequential decision making that captures correlations across instances and also gives like statistical regret bounds interpolating between the adversarial and the stochastic case. It gives efficient reductions from sequential decision making to optimization, which is maybe I'll skip this for now and maybe quickly mention other sort of settings where this leads to some interesting results. The first one is discrepancy minimization. In online discrepancy minimization, you get vectors online and you need to assign signs. You can show like against an adaptive adversary, you can't get any like you can get only trivial sort of discrepancy bounds. We can show that against an adaptive adversary with some smooth model, you can still get bounds that are analogous to the average case. And similarly for results about data-driven algorithm design, and we have some forthcoming work on like solving sequential games under the smooth setting where you can get faster convergence to equilibria. Anyway, I presented the smooth adversary model, which gives us a framework for statistical and computationally efficient algorithms for sequential decision making. Yeah, thanks for your attention, and I'll take any questions.
So question, so if the noise is like exponentially small in like the Littlestone dimension.
Sorry, I can't hear you. Yeah.
Can you hear me now?
Yeah.
So I'm asking if the noise is like exponentially small in the Littlestone dimension, your algorithm does like worse than that, like the.
Oh, so there are min of Littlestone dimension terms everywhere. I mean, the thing is, you could in online learning, if you don't care about log terms, you can always hedge between two algorithms and get like regret bounds at best. I mean,
thanks.
Sorry, square root on T Oh yeah, that's actually an interesting question. We have some lower bounds that says there's a computational statistical gap. There is for some regime of sigma, we can show that the polynomial dependence on sigma is essential. It is open in some sense to get a satisfactory computational statistical gap. There are some you can prove some query complexity lower bounds that say that For some sigma that you need a polynomial dependence on sigma computationally efficiently, and statistically it's a logarithmic dependence, but yeah.
Okay, so let's thank Abhishek again and can have a coffee break.
I'll just leave this here. I'll just leave this here. Oh, I'll switch it off. Okay.